In this video, we're going to look at a new example of the Green's function. So we're going to take a fourth order ODE, constant coefficients, but with non-homogeneous forcing term. As a first step, we're going to solve the homogeneous problem. And I'm not going to be going into details. You apply the characteristic polynomial and you're happy. And then the step 1, we're going to be replacing the forcing term, whatever that is, with the Dirac's delta function. So now we have a new non-homogeneous ODE with the same characteristic as the previous ODE, but now with a fixed right-hand side that we have just chosen. And we're going to be solving this new ODE and use the result to solve the general ODE with the non-homogeneous right-hand side that was chosen at the beginning. So in order to solve this new ODE, we're going to apply the Laplace transform on both sides. We're going to use the standard notation that capital Y is the Laplace transform of Y. So because we're looking for a particular solution, we're free to choose boundary conditions or initial conditions. So in here, I'm going to be choosing that all y computed at 0 and all its derivatives that we're interested on are set to be 0 at 0. So here we don't have to keep track of all those terms. And we retrieve that the Laplace transform of both sides is s to the fourth capital Ys minus 3 capital Ys equal the Laplace transform of the delta function. Laplace transform of the delta function being the exponential of minor tau s. So capital Y is equal to a fraction between the Laplace transform of the delta function and the characteristic polynomial. Now we want to apply the inverse Laplace transform to this fraction. We could go in the direction of saying that the inverse Laplace is the convolution of the Laplace transforms, but we also know that when we have exponential of minus tau s, we retrieve exactly the Heaviside function on the other side with a shift in time, and the inverse Laplace of only the fraction part. So we're going to be solving that. We're going to use partial fractions to simplify 1 over s4 at the minus 3. We're going to split it as s2 at the minus square root of 3 times s2 plus square root of 3, and then we subdivide it even more in s minus 3 to the 1/4, so double square root of 3, s plus 3 at the 1/4, s minus imaginary number times 3 at the 1/4, and s plus imaginary number of 3 at the 1/4. So we are going to split this in 4 simpler fractions. A over s at the 3 at the 1/4, b over s plus 3 at the 1/4, c over s minus imaginary number times 3 at the 1/4, and d over s plus imaginary number of 3 at the 1/4. We're gonna multiply the everything, the left-hand side and the right-hand side, by the denominator of a, capital A, and we're gonna set s equal to 3 at the 1/4, such that the denominator of a is equal to 0. If we do that, things simplify a bit. We notice that all the terms that involve b, c, and d are multiplied by something that we have just set to 0, so they disappear. And the left-hand side can be computed to be 1 over 2 times 3 at the 1/4 times parentheses 3 at the 1/4 plus 3. We can do the same trick for b, c, and d. Therefore, we have explicit formulas for a, b, c, and d. You might be confused by the fact that c and d are over a complex polynomial, but if you go through the steps, you're going to notice that the complexity actually cancels out easily. So now we have the inverse Laplace of 1 over s to the 4th minus 3 being the inverse Laplace of the sum of 4 fractions, and therefore being the sum of 4 inverse Laplaces of each simpler fractions. So we apply this, and because the fractions are so simple, we can remind ourselves that the inverse Laplace of 1 over s minus a is e at the at. So we retrieve things fairly easily. we have here an exponential of the imaginary number, but we have the Euler's formula and that simplifies. And by how we have computed c and d, you will notice that the sum of c times cosine of things and d times the other things cancel out all the imaginary parts. So we are again with a real solution. So for the situation in which we have fixed the right-hand side to be the delta function, we can compute the partial solution of our problem. This is what we call the Green's function. It's a bit messy, it has lots of terms, but we have it. And once we have the Green's function, we know that the partial solution to any other problem based on the same ODE with different forcing terms is the convolution of the forcing term that you're given and the Green's function. So in our case, when the forcing term was cosine 3t, then our partial solution is the convolution of cosine 3t and the Green's function that we just computed the previous page. And the global solution, so the solution that is the sum of the homogeneous and the partial solution, it's something that we can again compute.